Yes, hello everyone. Welcome to OHM Institute. I am Surendra Reddy, Faculty for Electrical Machines at OHM Institute, Hyderabad. So, the response sheet has been released, TSGENCO Assistant Engineer Exam. And here I am going to discuss about electrical machines questions. So, we have 12 questions overall from electrical machines subject. So, I would say the questions are not so easy, at the same time they are not so difficult. I would say they are moderate level. So, those who have practiced numerical part of the subject well, they can easily answer all these questions. Okay, if you relied completely on theoretical part, you might find the subject is slightly difficult, but those who have practiced numerical questions sufficiently, they can easily answer the questions. Okay, all right, so let us go through the first question. This is a question from DC motors. A 250 volt DC shunt motor takes a current of 41 ampere and runs at 800 rpm on full load. The armature and field resistances are given 0.2 ohm and 250 ohm respectively. During stalling of the motor, a resistance of 2 ohm is placed in series with armature. Then what is the ratio between stalling torque to motoring torque? See, the question is about ratio from stalling torque to motoring torque. Okay. So what I will do is that first I will consider the motoring mode and I will try to calculate what is armature current. Then I'll consider stalling mode and I'll calculate armature current in that mode as well, because we all know that torque equation in DC motor is Ka phi into Ia. And as it is a shunt motor, flux is always a constant value. If a flux is a constant value, torque is directly proportional to armature current. So if I wanted to find out ratio from stalling torque to motoring torque or full load torque, indirectly this is going to be the ratio from stalling armature current to motoring armature current. Okay, that's all. So if I know these two currents, I can find out the ratio between stalling torque to motoring torque. Okay, so first I'll try to find out motoring current, because already the motoring details are given. What is the current drawn by motor? 41. Out of that 41, some current will go to the field also. So let's try to find out. So in the motoring mode, yes, the terminal voltage of the motor is equal to 250, right? 250 volt. The total current drawn by motor is 41 ampere. That is nothing but the line current drawn from the source. Out of that 41 ampere, how much will go to the field circuit? Yes, what is the formula for field current? Vt by Rf. Vt is 250. Field resistance is also 250. Therefore, 1 ampere will go to the field. That means the remaining current will go to armature. So armature current is line current minus field current. So 41 minus 1, that is equal to 40 ampere. So this is armature current in motoring mode. So I need to calculate what is armature current in stalling mode also. Yes. What is mean by stalling mode? Stalling mode or breakdown condition, both are same. Stalling condition means it is the position where a rotor stops rotating. Okay. If rotor stops rotating, the speed will be equal to 0, right? If speed is equal to 0, then back EMF will also be going to be 0. What is the formula for back EMF in DC motor? Ka phi into omega. If omega is 0, back EMF is equal to 0. If back EMF is 0, then what is the formula for armature current? It is simply Vt divided by Ra plus R external. Actually, the formula is Vt minus Eb, but here Eb is equal to 0. That's why I'm not writing. Anyway, I can write that. Vt minus Eb by not only Ra, some extra resistance is added in armature circuit. That was clearly mentioned in the problem, right? 2 ohm extra resistance is placed in series with armature. Okay, so find out now. Vt 250, back EMF is 0, divided by armature resistance is 0.2, extra resistance is 2 ohm. So it is 250 divided by 2.2. This is armature current in which mode, guys? Stalling mode. Now I can find out ratio between stalling torque to motoring torque, which is stalling current by motoring current. I can directly substitute here. Stalling current is 250 by 2.2. Motoring current is 40. Okay. So if you calculate, the denominator is 2.2 into 40, that is 88. So it will be 250 divided by 88. Okay. Suppose if I assume 88 is nearest to 90, then it will be 250 by 90. Okay, so then answer will be 2 point something. The nearest answer will be 2.84. Yes or not? Okay. So that's it. So this is the answer for the first question. What is the ratio between stalling torque to motoring torque? It's simple. You just calculate motoring current, you calculate stalling current, and take the ratio, you'll get stalling torque to motoring torque ratio. So the answer is 2.84. Okay. No need to calculate the answer till the fractions. You just try to take the approximations. 250 by nearest to 90. 250 by 90 means more than 2, less than 3. So the only option is 2.84. Okay. Right. Fine. So we have another question from DC machines. Okay, just to read the problem. The self-excited DC generator failed to build up the voltage at no load. Okay, it was clearly mentioned. Self-excited machine will fail to build up the voltage at no load. Identify the correct reasons from the following. So we have to identify the reasons for failure of EMF in DC self-excited generator. First of all, what are the conditions to be satisfied to induce EMF? Yes, to induce EMF, what are the conditions to be satisfied in a self-excited DC generator? That means you can consider DC shunt generator. Okay, yes, the first rule is residual flux is mandatory. Residual flux is mandatory. This is compulsory. Okay. Second rule is field winding connection. Correct field winding connection is important. Correct field winding connection. So if you use correct connection, then only additional flux will magnetize residual flux and resultant flux can increase. Okay. So correct field connection is important. And the third rule is field resistance must be less than critical resistance. Field resistance must be less than critical resistance. Field resistance must be less than critical resistance. If it is more than critical resistance, only residual EMF can be generated. Okay. And the fourth rule is speed must be less than critical speed. Sorry, speed must be more than critical speed. Speed must be more than critical speed. If any condition out of these four failed, definitely the machine cannot develop any EMF at no load. Okay. So the question is about which condition will fail to build up the voltage. Then definitely the first one is correct. If a residual magnetism is absent, definitely machine will fail to build up the voltage. Field resistance less than critical resistance means voltage will build up. Okay. But it will not build up means it is wrong statement. Speed of the armature is more than critical speed means yes, voltage will build up, but not build up means it is wrong answer. Field resistance is more than critical resistance. Yes, if field resistance is more than critical resistance, development of EMF is not possible. Next, speed of the armature is less than critical speed. Yes, in this case also development of EMF is not possible. So we are asked to find out failure conditions, not successful conditions. I told you successful conditions here, therefore failure conditions are exactly opposite. So 1, 4, 5 statements are correct. This is the third option. Okay, easy question. Okay, now we have the next question. This is from transformers. Read the problem. A 11,000 by 2,200 volt 100 kVA single phase 2 winding transformer is to be used as auto transformer by connecting the two windings in series. Which of the following are not possible values of voltage ratios and kVA outputs of the transformer? Which of the following are not possible? That is what you need to be very clear with. That means wrong answers you have to select. Okay. First of all, when a 2 winding transformer is converted into auto transformer, the value of K is very important to identify VA rating. What is the formula? VA rating of auto transformer is always equal to 1 by 1 minus K times of VA rating of 2 winding transformer. This is the formula, right? Where K is nothing but low voltage value by high voltage value of auto transformer. Clear? Okay. Now, if you look at the 4 options given here, 2200 by 13,200 and also 13,000 by 2,200. Remember guys, in a transformer, Yes, whether it is a step up connection or step down connection, VA rating will be same, right? Whether it is from low voltage side or high voltage side, VA rating will be same. That means 2200 by 13,200, 13,200 by 2,200, both will have same VA rating. Let us calculate that, okay? I will consider the first one, 2,200 by 13,200. 2,200 by 13,200 volt. That means what is the value of K? K is always LV by HV, as I mentioned. That is 2,200 by 13,200. Two zeros will cancel. It is 22 by 132. That means 2 by 12, which is 1 by 6. Am I correct? Okay. So this is K value. Therefore, what is the VA rating? VA rating of auto transformer is 1 by 1 minus K into VA rating of 2 winding transformer. Just to substitute 1 by 1 minus 1 by 6 into what is the VA rating of 2 winding transformer? 100 kVA. 100. So it will be 6 by 5 into 100. 5 will cancel 20 times here. Therefore, 120 kVA is the answer. So 2200 by 13,200, 120 kVA. 2200 by 13,200, 120 kVA. Therefore, this is a correct statement, but we have to answer wrong statements here. Also remember, 2200 by 13,200 and 13,200 by 2,200 will have same VA rating. That means 1 and 3 both are correct statements. But I have to answer the wrong statements only. Now let us select the second one. 11,000 by 13,200. Okay. 11,000 by 13,200. If this is auto transformer ratio, then calculate K again. K is always LV divided by HV. 11,000 divided by 13,200. Two zeros will cancel. 110 by 132. That is 10 by 12. Okay. 5 by 6. This is the value of K. The moment I know K value, what is the VA rating of auto transformer? 1 by 1 minus K into VA rating of 2 winding transformer. Just a substitute. So 1 by 1 minus K is 5 by 6. 2 winding transformer is 100. So the answer will be 6 times 600 kVA. Yes or not? 1 by 1 minus 5 by 6 means it will be 6 times. So 600 kVA. So 11,000 by 13,200, 600 kVA, that is correct statement. I also told you that 11,000 by 13,200 or 13,200 by 11,000 will have same answers, right? Okay. Therefore, what is the only wrong answer here? Yes, this is the wrong answer, right? This is wrong. Wrong means this is your selection, because the answer is what is not possible. 2,200 by 13,200 means 120 kVA is correct, 600 kVA is wrong. I think just by answering this one statement, you can pick up the answer. Why? Because 2,200 by 13,200, 120 kVA, but this is showing 600 kVA. You need not to select the other options. Directly, this is going to be the wrong answer. Okay. Within 1 minute, you can answer that question. Okay. Next, we have a question from a transformer again. This is a theoretical question. Just to read the problem. Delta star connect. Which of the following statements are not correct? Please be very careful. Okay. Presence of mind is very important. Generally in exams, most of the examiners will ask what is the correct answer, but here they are asking what is the wrong answer. Okay. Not correct. So delta star connected 3-phase transformer is used in the beginning of a HV transmission line. Remember guys, beginning of HV transmission line means it must be a step-up transformer. Right or not? Step-up transformer. Right? High voltage transmission line means you have to step up the voltage and then give that voltage to transmission line. Yes, what is the best transformer which can be used as a step-up connection? Delta star. Okay. If it is step-down transformer, you must use a star delta. So therefore, first statement is correct statement. Delta star is used for step-up applications, which is a correct statement. Therefore, that is not my answer. Okay. This is a correct statement. Okay, let's see the second statement. Open delta connection is not possible with star-star connected 3-phase transformer. Yes, it is correct. Why? Because open delta connection means I don't need 3-phase transformer, guys. I need 3 single-phase transformers. If it is a single 3-phase transformer, we cannot create open delta connection. We need single-phase transformers, at least 2 single-phase transformers I need, so that I can form open delta connection. Therefore, not possible is a correct statement. Okay, yes. Next one. Star delta connection is used in 3-phase distribution transformers. Yes, this is a wrong statement. Why? Because distribution transformers are always delta star type, guys. Okay, why? Because load distribution means 3-phase load will be available, single phase load will also be available. Therefore, you definitely need a star connection on the secondary side, then only 3-phase load and a single phase load can be combinedly fitted at the same time. Okay, therefore distribution transformer means it must be a delta star transformer, but here is they said star delta, that's why third statement is a wrong statement. Fourth one, oscillatory neutral problems are not present in star star connection. This is a wrong statement. Why? Because if it is a star star connection, definitely oscillating neutral concept will come into picture. Okay, those who attended class generally they will study this. Okay, if primary is a star connection, secondary is also a star connection. Okay, in this case third harmonic magnetizing current cannot circulate. If a third harmonic magnetizing current cannot circulate, flux becomes non-sinusoidal. The moment when flux becomes non-sinusoidal, it can be resolved into 2 components, fundamental flux and third harmonic flux. Fundamental flux will create E1, third harmonic flux will create E3. Because of the presence of E3 component, neutral potential is going to oscillate. Understand? Therefore, star-star connection means neutral will oscillate definitely. And how to avoid that oscillating neutral? Yes, the oscillating neutral we can avoid by using a tertiary delta connection. Okay, yes, by using a tertiary delta connection, we can circulate third harmonic current so that oscillating neutral can be avoided. That means this statement is wrong. Star-star connection means oscillating neutral will definitely present, but they said not present. That's why this is a wrong statement. So finally, what are the wrong statements in the entire question? Third one and fourth one are the wrong statements. Okay, we have to select wrong statements, guys. Okay, fine. We have another question from transformers. Read the problem. A 10 ohm resistive load is to be impedance matched by a transformer to a source with 6250 ohm of internal resistance. The ratio of primary to secondary turns of the transformer is how much? Okay, very simple question. There was a source with the internal resistance of 6250 ohm. Now, by using a transformer, I have to match a 10 ohm resistance with this 6050 ohm resistance. Okay, this is 10 ohm. Okay, so we have to match this 10 ohm resistance with 6250 ohm resistance. That is what we call it as impedance matching transformers. Okay, now imagine the turns ratio of this transformer is N1:N2. Now what you do is that just transfer this resistance to primary side. The moment I transfer this resistance to primary side, it should match with 6250. Okay, we all know that when RL is transferred to primary side, can I say its value will become RL dash, and then that RL dash should match with 6250. Therefore, 6250 must be equal to RL dash. Okay, now what is the formula? 6250 is equal to what is RL dash? It was shifted to primary. Primary means N1/N2 whole square into RL. So 6250 is equal to N1/N2 whole square times of RL is 10 ohm. Yes. So therefore N1/N2 whole square is equal to 625. That means N1/N2 is equal to 25. This will be the turns ratio of the transformer. Okay, impedance matching application. So the load impedance has to be matched with source impedance. That is where transformer action will come into picture. Okay, easy question. So the turns ratio of the transformer must be 25:1 so that load impedance can be matched with source impedance. Okay. Okay, so we have another question. This is a compound generator. Once again, the question is from DC machines, DC compound generator, and that too a short shunt compound generator. Okay, it is supplying a load current of 100 ampere at 250 volt. The generator has the following winding resistances: shunt field resistance 130, armature resistance 0.1, series field resistance 0.1. Find EMF generated if the brush voltage is 1 volt per brush. So we are just asked to find out what is generated EMF. Yes, what is the formula for generated EMF in compound machine? It is Vt plus IaRa plus series resistance drop ISE RSE plus overall brush drop Vb. But as it is a short shunt compound generator, first you should have idea about short shunt compound diagram. Imagine this is the armature circuit EG. Short shunt means first shunt field winding will be connected and later the series winding will be connected like this, and finally we have the load branch here. Okay, this is load current, this is series resistance, series current, this is shunt resistance, and this is shunt current, this is armature current. Now voltage across the load is what we call it as terminal voltage. Now you can clearly understand from this diagram that load current and series current both are absolutely same. What is the load current? 100 ampere. That means series current is also 100 ampere. Now calculate shunt current. What is the formula for shunt current? Shunt current is equal to Vt plus ISE RSE by RSH. So what is Vt? 250 plus ISC and IL both are same, 100. What is series resistance? 0.1 ohm divided by shunt resistance is equal to 130 ohm. So 100 into 0.1, 10, 250 plus 10, 260 by 130, this is 2 ampere. 2 ampere will go to shunt field. Then how much will go to armature? Therefore, armature current is equal to load current plus shunt field current. 100 plus 2, therefore armature current is 102 ampere. The moment I know armature current, I can calculate generated EMF. So formula, generated EMF is equal to Vt plus IaRa plus ISE RSE plus brush drop. Vt 250, armature current is 102, armature resistance 0.1, series current also known as load current, same 100, series resistance 0.1, brush drop 1 volt per brush, 2 brushes will be there, therefore 2 volt. 2 brushes drops we have to consider while calculating voltage. So 250 plus 10.2 plus 10 plus 2, so overall it is 272.2, right? 272.2 volt. That is the generated EMF. So I think last option 272.2. Yes, this you have to calculate the answer completely. Why? Because the options are very close. Okay, and it don't take much time. You should not feel this question is difficult if you really know the formulas well. If you had really good practice earlier, these kind of questions you can easily answer. Okay, right. All right. Now we have a question from synchronous machines. This is a theoretical question. Identify incorrect statements. Again, you need to be very clear. Incorrect statement. That means wrong statements I have to identify. In round rotor synchronous motor, reactive power is maximum at a load angle of 90 degrees. This is a wrong statement. Why? Because we know reactive power will be maximum at 90 degrees or 0 degrees. Yes, 0 degrees is correct. Okay. Active power will be maximum at 90 degrees. Reactive power will be maximum at 0 degrees. Therefore, first statement is a wrong statement. Damper winding is provided in a polyphase synchronous motor in order to provide a starting torque. Yes, this is a correct statement. Damper winding will have two main damper winding will have two main functions in synchronous machines. First one is to create starting torque for synchronous motor, and second one is to reduce the hunting phenomena. Okay, so it will create starting torque in synchronous motor. That is absolutely correct. Next, in a slip test on a salient pole synchronous machine, the EMF induced in the field winding is 0 for XQ, quadrature axis. See, it is a slip test. Slip test is performed on salient pole machine, we know. This is how the rotor looks like. This is the field winding. And they said flux is along which axis? Quadrature axis. Okay. Quadrature axis means we know this one. This is Q axis. Now tell me what is the angle between flux line which is along Q axis and rotor field winding which is vertical. See, rotor is vertical, flux is horizontal. Can I say there is 90 degrees between the two? When angle between conductor and flux is 90 degrees, then maximum EMF will be induced in rotor. Okay. So here maximum EMF will be induced, but they said 0 in the question. That's why it is a wrong statement. Okay, very simple thing. We are asked to find out EMF not in stator but in rotor, field winding. Field winding is here on the rotor. You can see field winding is vertical, but flux is along quadrature axis which is horizontal. The angle between the field winding which is vertical and field along quadrature axis which is horizontal, therefore 90 degrees means maximum EMF will be induced. You can apply the formula BLV sin theta. If theta is 90 degrees, maximum EMF should induce, but they said 0 EMF, which is a wrong statement. Okay. Next, synchronous condenser is an over-excited synchronous motor driving a mechanical load. This is wrong. Why? Because they are talking about a synchronous condenser. We all know that synchronous condenser means it is an over-excited synchronous motor operating at no load. But it is given driving some mechanical load. That is absolutely wrong. So, the wrong statements here are 1, 3, 4. 1, 3, 4 are the wrong statements. Second one is correct statement. Okay. Fine. Now next we have a question from induction motor, and it is an easy question. The time period of rotor current of a 4-pole 50 Hz induction motor is 200 milliseconds. What is the slip speed of the motor is the question. See, rather than giving a rotor frequency directly, the time period was given. If rotor time period was known, can we calculate rotor frequency from that? Yes. We all know that frequency is equal to 1 by time period. Therefore, rotor frequency is equal to 1 by time period of rotor. What is the time period given? 200 milliseconds. That is 200 into 10 power minus 3. That is 1 by 0.2, which is equal to 5. Therefore, rotor frequency is equal to 5 Hz. If we know rotor frequency, how can we calculate slip, guys? We all know that rotor frequency is equal to slip times of supply frequency. So from this, slip is equal to rotor frequency by supply frequency, 5 by 50 Hz, 1 by 10, that is 0.1. Slip is 0.1. If I know slip, how to calculate a slip speed? They are not asking about slip, they are asking about slip speed. Yes, what is the slip speed? We know slip speed is nothing but S into Ns, also known as Ns minus Nr. That is nothing but slip speed. So if I continue, S is 0.1, Ns 120 F by P, that is 120 into 50 by 4 poles, 150 RPM. Because 120 into 50 by 4, 1500. 1500 into 0.1, 150 RPM. Therefore, the answer is 150 RPM, slip speed. Okay. Yes. Next, we have a question from synchronous machines again. The following notation will represent what? Is it motor or generator? First question. It is under-excited or over-excited? Second question. How do you decide whether it is motor or generator? Yes, based on EF leading or VT or lagging VT. If you look at the diagram carefully, this is VT, guys, and this is EF. So easily we can conclude that EF is leading VT, right? EF is leading VT. EF is leading VT means definitely this is an alternator. Only in generator EF will lead VT. Suppose if it is motor, EF will lag VT. Next question. How do you decide whether it is over-excited or under-excited? Two ways you can decide. One is by comparing EF cos delta with VT. Another one is power factor. You can see here, armature current was here, guys. Therefore, can I say armature current was definitely leading terminal voltage? Therefore, IA is leading VT. That means power factor is leading power factor. Okay, leading power factor means it is under excited. This is one way to understand it. There is another procedure that is from the phasor diagram. Okay, you see that this is EF phasor, right? From EF phasor, draw a perpendicular line like this. Make sure there is 90 degrees. Okay, now we all know angle between EF and VT is nothing but delta. Therefore, if you look at this right angular triangle, can I say this distance is nothing but EF cos delta? Okay. Now you compare this EF cos delta length with overall VT length, I can easily understand EF cos delta is less than VT. EF cos delta less than VT, this is another condition where you can conclude it is under excitation. Under excitation means EF cos delta less than VT, over excitation means EF cos delta greater than VT. This is one more way you can conclude it is under excited. Under excited alternator because EF is leading VT. Okay. Fine. Now we have another question. This question is from induction machines. Another easy question I can say. Cogging and crawling are less prominent in slip ring induction machine. This is a correct statement. We know in a slip ring induction machine, you can overcome cogging and crawling by adding external resistance into rotor circuit. When external resistance is added into rotor circuit, starting torque will be increased. You can easily overcome the cogging phenomena. Whereas in a squirrel cage induction motor, we can't overcome. Therefore, cogging and crawling are very serious in a squirrel cage machine, but not so serious in slip ring machine. Therefore, this is a correct statement. Okay, the next statement. Induction harmonic torque can be reduced by skewing. Okay, induction harmonic torque are also known as asynchronous harmonic torques. Anything is same. Asynchronous harmonic torques. Yes, asynchronous harmonic torques are the main reasons to create crawling phenomena in induction motor. And by using a skewing mechanism, we can reduce these harmonics effect. Therefore, second statement is correct. Skewing is one of the procedure to reduce the effect of harmonics so that crawling and cogging can be minimized. Next, synchronous harmonic torques. Yes, synchronous harmonic torques means slot harmonics mainly. Slot harmonics. Okay, slot harmonics can be avoided by proper combination of stator and rotor slots. Yes, this is also correct. And I told you slot harmonics are also one of the reason to produce, cogging and crawling phenomena in induction motor. See, because of harmonics only, cogging and crawling phenomena will take place. There are various techniques to remove harmonics from induction machine. Short pitch winding, fractional slot pitch winding, skewing, distribution of the winding, and proper selection of stator and rotor slots. Okay. Yes, what are the combinations we should never try in induction motor? Number of stator slots should never be equal to number of rotor slots. If slots are equal, cogging will come. Also, the difference between stator slots and rotor slots should never be equal to integral multiple of poles, and also the difference should not be equal to number of poles. If you avoid these designs, cogging and crawling phenomena can be avoided. Therefore, third statement is also correct. That means they are asking correct statements. That means 1, 2, 3, all three statements are correct. Okay. Next, a three-phase transformer bank consisting of 3 single-phase transformers. It is used to step down the voltage of 3-phase 6600 volt transmission line. Primary line current 20 ampere. What is the kVA output if the connection is star delta? See, input line voltage was given. By default, we know given voltage is always line voltage. So the input line voltage is 6600 volt. And also the line current was given. Primary line current, also known as input line current, that is equal to 20 ampere. What is the kVA output? We all know in a transformer, output kVA or input kVA both are same. So if I calculate input kVA, that is also equal to output kVA. So therefore, what is the VA rating input side? √3 VL IL. Definitely I can use this formula because it is a three-phase connection. So √3 into what is the line voltage? 6600. What is the line current? 20. These 2 zeros and 1 zero will give you kVA rating. Therefore, finally it is root 3 into 66 into 2 kVA. What is 66 into 2? 132. So it is root 3 into 132 kVA. Remember guys, this is input kVA. Then what about output kVA also? Same, because in transformer, volt ampere rating is same on input side and output side. So it doesn't matter whether it is star delta connection or delta star connection, the VA rating remains the same, root 3 into 132 kVA. So first statement is correct. Okay. Now the next question, this question is from induction motors, especially from starters. If you read the problem, a 3-phase 4-pole 50 Hz induction motor has full load speed of 1425 RPM and takes 6 times the rated current under blocked rotor test. Blocked rotor test means short circuit current. When the starter using auto transformer with 50% tapping, what is the ratio between starting torque to rated torque? First of all, I will use this full load speed and let me calculate full load slip. What is the formula for full load slip? Ns minus Nr divided by Ns. What is Ns in this question? 4-pole 50 Hz, that means 1500 minus 1425 divided by 1500. This is like 75 by 1500, which is 1 by 20. Keep it like that, 0.05. This is full load slip. And what is a short circuit current? 6 times. It is given short circuit current is equal to 6 times full load current. We know blocked rotor test is equivalent to short circuit test. Also, the tapping is 50%. X value 0.5. If you know all these details, then what is the ratio from starting torque to full load torque? Yes. So starting torque divided by full load torque, direct formula guys, x square into ISC by IFL whole square into slip at full load. What is x? 0.5 square. ISC is 6 times IFL whole square into slip at full load 1 by 20, right? 1 by 20. So it is 0.25 into 36 into 1 by 20. Can I say 0.25 is 1 by 4? Therefore, it is 36 by 4 into 20, 80. Okay. Now you can choose the nearest answer. Okay, 36 by 80. If it is 36 by 100, 0.36. 36 by 80 means more than 0.36. Okay. So it will be 45%. 36 by 100, 0.36. 36 by 80, more than 0.36. That means more than 36%. Therefore, the nearest answer is more than 36%, 45%. Okay. That is how you need to answer. No need to solve till the end. Sir, 36 by 80 require calculator. I don't have calculator in exam. That is a wrong statement, wrong way of understanding the exam. So nobody will give you calculator. You should calculate 36 by 100 if I take 0.36. As it is 80 only, definitely more than 0.836. More than 36% percentage wise, the nearest value 45%. Okay, that is the ratio from starting torque to full load torque or rated torque of the given induction motor. Okay, that's all. These are the 12 questions that we got from induction synchronous DC transformers together. There are no questions from special motors, as I explained earlier in many of my videos also. In AE exam, there won't be much questions from special motors, even if you get 1 or 2 questions only maximum. But in this exam, there were no questions from special motors. Okay, so that's all. I would say moderate exam. It's not so difficult. Okay, it was moderate. You can spend hardly around 10 minutes to solve these 12 questions if you had good practice. Okay. Also, one point I would like to mention, all these questions are available in my classroom handouts. If you can correlate, I'll do a special video. I will explain which handout, which question number is matching with this question. I won't say exactly word to word it is matching. The concepts are matching, almost 90% matching is there. Okay. Most of the questions are coming from handout only. So classroom handouts are extremely important for those students who are aiming for assistant engineers exam. Okay. All right. Thank you so much.